Here we're going to discuss approximating the value of convergent alternating series. We start out by talking first realizing that we can approximate the value of any convergent series by using a partial sum. And as I stated here, look, as an example, we know that the series of 1 over n squareds, which is a p-series where p is equal to 2 and greater than 1, we know that this converges. At this point, we have no idea what it converges to. But for instance, we could look at the partial sum, let's say s sub 10, which would mean that we're going to add up the first 10 terms. The sum from n equal 1 to 10 of 1 over n squared. And of course, we know that that would be, when n is 1, that would be 1. When n is 2, that would be 1/2. When n is 3, then that would be 1, excuse me, my bad. When n is 2, that would be 1/4, wouldn't it? And when n is 3, that would be 1/9. And when n is 4, that would be 1/16, and we can continue doing this until we get to where n is 10, and that would be 1 over 100, wouldn't it? Okay, so we could add those up, and that would at least give us some approximation. And in fact, in this case, when I added these fractions together, I got approximately 1.549767731. But unfortunately, I have no idea how good of an approximation that is. Since I don't know the value of the original sum, the infinite series, I have no idea how good of an approximation this is. I can approximate further. I could say, well, let's look at the 100th partial sum. And of course, that would be the sum from n equal 1 to 100 of 1 over n squared. And I could add these up. And in fact, I used my calculator to do just such a thing. And when I did, I got approximately 1.63498390. Now, certainly that's an approximation, but when we're adding to infinity, we're adding an infinite number of terms beyond what we have here. And so, once again, we have no idea of how close this approximation is to the actual value. Well, I will tell you this, and we have no reason to know this right now, and it's not really related to what we're doing, but the actual sum of this series is pi squared over 6, which if we approximate that, using an approximation for pi, we get 1.644934068. Of course, we're getting closer to that value, but we're still a significant amount away. I mean, this is, when we add up the first 100 terms, you see that we're only within 1/100th of the actual value, and in some cases, that's not nearly accurate enough. So, and we would have had to know what that original sum was to begin with anyway to know how close we were. Well, here's the deal. With convergent alternating series, we actually have a way to know how accurate our approximation is. Even though we don't know the value of the sum, the infinite sum, we can predict how close our approximation is to the infinite sum. And it's called, we do this dealing with the remainder. So let me set some things up here with a little pause. Okay, as you see here, we're going to now assume that we have an alternating series. The sum from n equal 1 to infinity of -1 to the power n plus 1 times a sub n, for which the limit of the a sub n's as n goes to infinity is 0, and each next a sub n is getting smaller than the previous. That's the a sub n plus 1 is less than or equal to a sub n's. That is, the a sub n's are getting ever smaller. In other words, as I've said here, the series converges. Those are the conditions we have to show true to be sure that an alternating series converges. Now, let's do this. since it converges, then it has some value. That infinite sum has some value. So let's let S represent the sum of all terms, okay? Which is, of course, the sum of the series. So that's exactly the sum of the convergent series, n equal 1 to infinity of negative infinity there, negative 1 to the power n plus 1 times a sub n. Now, we don't know what that value is, but we're calling it S. And let's let S sub capital N be the sum of the first capital N terms. In other words, a partial sum. Sum of the first N terms. And we would write that in sigma notation as the sum from lowercase n equal 1 up to uppercase n of negative 1 to the power n plus 1 times a sub n. Okay, just the first capital N terms. Now, we're going to define the remainder. Here's what I mean by this. We're going to use S sub capital N as an approximation to the actual sum. Okay, but how much more is there in the actual sum than the partial sum? And we call that the remainder. In other words, the remainder, I'll call by R sub capital N, is the difference between the actual sum and the partial sum. So in some ways, then, R sub n is the deviation from the actual sum. That is the error our partial sum is from being equal to the actual sum. And what that would give us then would be a sum from n equal 1, from n equal n plus 1. See, because we're subtracting away the first n terms. And so we're starting with this remainder. We'll start with the n plus first term and go to infinity. Still an infinite number of terms because we're only subtracting away a finite number of terms. Now, let me make some room down here and make kind of clear what R sub n is in terms of this notation. So I'm going to start over here. R sub n is the difference between the actual sum and the nth partial sum. And if we look at this notation, remember what we'll have here is when n is capital N plus 1, then we put a capital N plus 1 into this position. So we'd have negative 1 to the capital N plus 1 plus a 1 times a sub n. And of course, that's capital N plus 2. And then we would add to that negative 1 to now the next one would be capital N plus 2 plus 1. So that's going to be a capital N plus 3. I'm getting to something here in a moment, so please bear with me. And then we would, except this would be, I've made a mistake here. Remember, lowercase n is n plus 1, and so our A would have a subscript of capital N plus 1, and this A would have a subscript of capital N plus 2. My bad the way I set this up. And then here we would have a negative 1 to the capital N plus 4 times A sub n plus 3, and then this would continue. Now, let me come down here again and let me rewrite this. In fact, let me write this on the next page. So excuse me while we pause to go to the next page, because this is critical in what we're going to do. Okay, I've rewritten it, and so it's a little more clear now too, and at the top of this page. And you see that R sub n is the sum of the terms starting with A sub n plus 1. Of course, we have this alternating piece with the negative 1 to a power. But R sub n represents how far away S sub n is from the actual sum. Now, I'm going to take this r sub n, okay? Remember that it's equal to this. But I'm going to take this r sub n, I'm going to look at the far right of this equation, if you will, and see that I have a negative 1 to a power, of course, in front of all of those. And what I'm going to do is I'm going to factor out a negative 1 to this first power, n plus 2, from all the remaining terms. And so I'll have an a sub n plus 1 in this place. And in this position, I'm factoring out a negative 1 to the n plus 2 power, so I'll just have negative 1 to the power 1. And so that's going to be a minus, negative 1 to the power 1 is negative, if you will, times a sub n plus 2, capital N sub plus 2. And when I look at this term, remember I'm factoring out a negative 1 from right here to the power n plus 2, so I'll just have left over a negative 1 to the power 2, which of course is positive. And so this will be plus a to the subscript, a with the subscript of capital N plus 3. And this will continue as we go through here. So my next term, after I factor out negative 1 to the n plus 2 power, will be a sub capital N plus 4. And then plus a sub capital N plus 5. And of course, this will go on now in an alternating pattern, which is not surprising. Okay, so here's what I'm going to do next. And by the way, before I go much further, let me suggest to you here that, of course, we don't know whether capital N is an even or an odd integer. So we don't know if negative 1 to the power capital N plus 2 is going to give us a positive result or a negative result. But if we look inside these brackets, here's what I want you to notice. That inside these brackets, if I look at these first two terms right here, remember the terms are getting smaller. So when I take a sub n plus 1 and I subtract a sub n plus 2, that's going to be a positive result. And over here, when I take a sub n plus 3 and subtract a sub n plus 4, because a sub n plus 4 is smaller than the previous term, then that's also going to be positive. And if we look all the way through here, we'll recognize that all of those are positive. Well, that's significant for my next step, because we don't know whether the remainder is positive or negative. And when we talk about the error, how far away we are, S sub n, how far away it is from the actual sum, then we don't really want to be concerned about, well, is it negative distance away or is it a positive distance away? So what we're going to do is we're going to consider the absolute value of r sub n, okay? The absolute value of the remainder, which is the absolute value of capital S minus the capital Nth partial sum. So because of what I've written, that's the absolute value of negative 1 to the power n plus 2 times, in these brackets, this a sub n plus 1 minus this a sub n plus 2 plus this a sub n, capital N, that is, plus 3 minus a sub capital N plus 4, and so on, that I'm running out of room over here for. Okay, so it's the absolute value of all of that. Well, the absolute value of r sub capital N, just rewriting the first couple of pieces of the previous line, the absolute value, remember what I said up here. In those brackets, all of that is positive. And outside of those brackets, I just have negative 1 to a power. And so that is going to be either a negative result or a positive result based on what type of exponent that in capital N plus 2 is. But regardless, the issue is, it's just going to be the value of this positive result. Remember, this is positive in here, just as we said before. So the absolute value of r sub capital N plus 1 is a sub capital N plus 1 minus a sub n plus 2 plus a sub n plus 3 minus a sub n plus 4 plus a sub n plus 5, and the pattern continues. Okay? So taking that absolute value, now we know that the remainder, if you will, r sub n, looks like what I've written. Now here's the significant part of this, and this is really important. When we look at this remainder, okay, let's look at these two terms right here. Now remember that the whole result is positive. See, remember this whole thing is positive when we add all those up, because we have an absolute value there. And so the whole thing is positive, but look what we have in this one position. A sub n plus 2 is bigger than a sub n plus 3, and we have a negative a sub n plus 2, and we're adding an a sub n plus 3, so the addition of these two terms along with that minus sign is a negative result. And the very same thing happens here. Here we get a negative result because a sub n plus 4 is bigger than a sub n plus 5. Remember, the a sub n's are getting smaller. And so since the negative a sub n plus 4, and we're adding a smaller a sub n plus 5, this result's negative. And that pattern is going to continue. The next pair is going to be negative as we look at that. And so what we see is that we're going to be adding a bunch of negatives to a sub n plus 1. So our conclusion then is this absolute value of r sub n being equal to what we have up there actually has to be less than or equal to a sub n plus 1. Because r sub n is actually a sub n plus 1 plus a whole bunch of negative pieces. Okay, and adding up all those negative pieces and adding that to a sub n plus 1, then we have to have something that's smaller than a sub n plus 1. So this is a big wow moment. Okay, let me rewrite this. The absolute value of the remainder, which is the absolute value of the difference between the actual sum and the capital Nth partial sum, is less than or equal to the first term that's beyond the partial sum. The entire, that's wow. Okay, if that hasn't hit home yet, wow. The entire remainder, or at least the absolute value of the entire remainder, okay, the entire remainder is less than or equal to the very next term. That's significant. Now, that tells us, okay, let's rewrite now. So that is, let's look at this piece right here, because this can give us a lot of information. In addition, is whenever we have the absolute value of s minus s sub n less than or equal to a number, that tells us, now remember, all the a sub n's are positive. The negativeness is done with that negative 1 to a power. So we have this absolute value is less than or equal to this next term, a sub n plus 1. Well, that means the s minus s sub capital N has to be less than or equal to a sub n plus 1, but also has to be greater than or equal to the opposite of it. It has to be between those two numbers. Now, if we will add this term right here all the way through, then we would get the nth partial sum minus the next term is less than or equal to the actual sum, which is less than or equal to the nth partial sum plus the next term. In other words, we can decide with an nth partial sum and its next term the bounds with which in the actual sum lies. So this is very important. Both of these things that we've written here are very important. Okay? And I guess when I say this is very important. this is very important. Well, that allows us to approximate how good using an nth partial sum, how close we get to the actual sum. And we're going to apply this right away. So as we pause and go to the next page, as you see here, the first example we're going to see using this approximation technique, we're to approximate the sum of, as you see, the series, which is -1 to the power n plus 1 times 1 over n factorial, by using its first 6 terms. Now, let's make clear that this technique works only with first convergent series. Sorry about that. With only convergent alternating series. It doesn't work if it's not alternating. It doesn't work, of course, if it's not convergent, because that doesn't have a finite sum. So the technique works only with convergent alternating series. And so it's imperative that we go through the check to be sure that the above series is alternating and convergent. And we have that. At least all, and I should even be more careful, the technique works only with convergent alternating series where it is true that the limit of a sub n as n approaches infinity is equal to 0, and all of the a sub n's are greater than or equal to 0 and getting smaller with each progressive n. Okay. I guess we could have a convergent alternating series that didn't satisfy these two conditions, or at least didn't satisfy the second condition. So we'd have to be careful here. But we're in good shape here. So that's, though, the first thing we have to be concerned about. Okay. So the first 6 terms would be defined, as we said before. It's actually the 6th partial sum, isn't it? And that would be the sum from n equal 1 to 6 of -1 to the power n plus 1 times 1 over n factorial. And so when n is 1, we would get -1 to the power 2 times 1 over 1 factorial. And 1 factorial is 1, so we'd get a 1 in that position. And then when n is 2, we'd have -1 to the power 2 plus 1, which would be -1. And then we'd have 1 over 2 factorial, and 2 factorial is 2 times 1, so we would just have 1 over 2. And then we would have, and I'll let you be concerned about the other terms, but then it'd be a 1/6 minus a 1/24 plus a 1 over 120 minus 1 over 720. And with my calculator, I approximated that to be 0.63194. Now that's an approximation to the actual sum. Now, how good is it? Well, it's within this distance. The next term, okay, the a sub n, not the negative part, the a sub n, is within this distance. So that would be 1 over, now remember, these are the a sub n's right here, okay? So it would be 1 over 7 factorial. And 1 over 7 factorial is 7 factorial is 7 times 6 times 5 times and so on, which ends up being 5,040. So this is 1 over 5,040, which is approximately 0.0002. So our approximation of 0.63194 is within 0.0002 of the actual value of the sum. So this is what we could say. Remember from earlier, we could say that, oh, well, what we know is if we subtract, well, this is what we had on the previous page. So let me write this in here. Remember well, I'll shut up for just a minute so I can finish writing this. This is the actual sum of the series. Okay. In our case, this is an S sub 6. In our case, this is an A sub 7. An S sub 6 and an A sub 7. So what this says is that S sub 6 minus A sub 7 is less than or equal to the actual sum, which is less than or equal to S sub 6 plus A sub 7. And S sub 6, remember, was 0.63194 minus A sub 7, which was 0.0002. Okay, and that's less than or equal to the actual sum, which is less than or equal to S sub 6, which is 0.63194 plus our A sub 7, 0.0002. And after my calculations, then this is 0.63174 on the left, less than or equal to capital S, less than or equal to 0.63214 on the right. And remember, this is the actual sum of the series from n equal 1 to infinity of negative 1 to the power n plus 1 times 1 over n factorial. So we don't know exactly what it adds to, but just with using the sixth partial sum, we see that it's between those two numbers. And that's a pretty darn good estimate, I would say. But we could have estimated it even to a greater level. In fact, our next example, what we'll do is we'll estimate to the level of accuracy that we desire. Okay, you can see stated here our second example. We're to determine the number of terms required to approximate the convergent alternating series. And remember, this is significant. It has to be a convergent alternating series that we have listed here, from some from n equals 0 to infinity of negative 1 to the power n divided by 2 to the n power times n factorial in the denominator, with an error of less than 1/1000th. That is 0.001, an error of less than 1/1000th. Now, there's a little bit of stuff going on here because we're starting our index at 0 rather than infinity, but all this really matters is this idea. The remainder, any particular remainder, okay, and we're looking for the correct remainder, the absolute value of the remainder is always less than or equal to the next left out term, if you will, okay, which a sub n plus 1 really is where the remainder starts. So here's the idea then behind this, and this follows generally. We need to find a situation where, because we're trying to have our error, and this represents our error, okay, from being exact, we need to find where a sub n plus 1 is less than or equal to 0.001. We need to find that term. And when we find that term, then that means then we should use n terms to approximate. So in this case, that would mean S sub n. See, here we have an s sub 0 and an s sub 1 and so on. And so s sub n would actually be the sum from lowercase n equals 0 to capital N minus 1, because we're talking about n terms. And so it's kind of off by a little bit of negative 1 to the power n over 2 to the nth times n factorial. But first things first, okay? First things first. So we're going to come through and we're going to start calculating these different a values. And we start out with a, and recognize, we need to recognize this, that a sub n is the stuff without the negative 1, isn't it? So it's 1 over 2 to the nth times n factorial. That's what a sub n is. So in the case of a sub 0, that would be 1 over 2 to the 0 times 0 factorial. And remember, 2 to the 0 is 1, and 0 factorial has special meaning, also 1. And so this is just 1. And then we'd calculate a sub 1. Now this is kind of what I would consider the take the bull by the horns method. I mean, I'm not sure if we can't get to this pretty quickly, then we're in trouble, because how far are we going to go to decide how to do this? But anyway, you know, what if we had to do this for 1,000 A's before we found one that was smaller than 0.001? This wouldn't be efficient, but let's try anyway. So a sub 1 will be 1 over 2 to the first times 1 factorial, which happens to be 1/2. Now I'm going to write this in decimal form, because what are we doing is we're comparing to 1/1000th, and so we're not there yet, are we? So now I'm going to calculate a sub 2, and remember what that is. I didn't write that before, but now our n is 2, so this is 1 over 2 squared times 2 factorial. And it's not difficult for us to figure out that that's 1/8. And as a decimal, that's 0.125. So we're still a ways away, aren't we? Well, I come in here and I calculate a sub 3 now. Well, a sub 3 is 1 over 2 cubed times 3 factorial. And when I calculate that, I get 1 over 8 times 6, which of course I can approximate as 0.0208. We're making a little headway, but we're still not there. A sub 4, well, of course, that's 1 over 2 to the 4th times 4 factorial. And that ends up being 2 to the 4th is 16, so that's 1 over 16 times 24. 24. And 16 times 24 is 384. So this is 1 over 384, which is 0 in decimal form, 0.0026. Aha. A sub 5 then. Well, a sub 5 is 1 over 2 to the 5th times 5 factorial. And that's 1 over 32 times 120. And that's 1 over 3,840. And that is equal to 0.0002 604. I was looking at my calculator. Okay. Now notice a sub 5, which is equal to this point 0.002604 is smaller than the amount of error that we desire to have. So that tells us what we were looking for, our n plus 1. See, that's what we're looking for up here. We need to find an a sub n plus 1 where its value is less than the error we desire. So that tells us our n plus 1 is 5, which in turn tells us the n we're looking for is actually 4. So to approximate within 0.001, we use the fourth partial sum. Okay, that's the sum in this case. That's the sum in this case from n equals 0 to 4, and I've kind of run out of room over here. You know what we've got there. So let's write it in here then. Our approximation is okay, the sum from n equals 0 to 4 of negative 1 to the power n plus 1 over I'm sorry, the infinite sum, okay, the infinite sum is approximately equal to, that's what we were looking for, the nth partial sum, in this case, that's 0 to 4 of those values. Which ends up being 1 minus 1/2. It's from above. That's the reason I put those fractions in there. 1 minus 1/2 plus 1/8 minus 1 over 48 plus 1 over 384. And that's approximately equal to 0.607. So we can use that approximation as our approximation for the sum of the entire series, the infinite series, and we know it's within 1/1000th of the actual value. So the only thing we would be off by would be this term. And we couldn't be more than 1 from that 7. Pretty amazing, isn't it? Well, on the next page, we'll do one last example, and we'll approach it a little differently. And by the way, we would say that this series converges quite quickly because we can get a fairly accurate approximation, you see here, with just the fourth partial sum. Sometimes a series converges much more slowly, and so we don't get close to a good approximation until we go much further out. And we'll see that in the next example. Okay, you can, as we read this third example, we're to determine the number of terms needed to approximate the alternating harmonic series to an error within 1/1000th again, an error less than 1/1000th. Okay, so what that means, once again, is we already know that this series is an alternating convergent series or convergent alternating series. And so what we're looking for is where a sub n plus 1 is less than or equal, oh no, not less than or equal to, that's a big deal here, okay? It's strictly less than 0.001. I didn't try this previously because the a sub n's were much more complicated and it was hard for us to do that. I just did it by brute force, looking at one example after another. And looking at one example after another here is going to be a little tedious because we would go a long way. But let's just recognize that a sub n plus 1 is pretty simple. A sub n plus 1 is really just 1 over n plus 1, isn't it? Okay, remember, these are the a sub n's, and those are the 1 over n's. So a sub capital N plus 1 is just 1 over that index, n plus 1. So that's what has to be less than 0.001. And we ought to be able to do something with this pretty easily, because what we could do, of course, is we could imagine 1/1000th written as, instead of this decimal, how about 1 over 1,000? And then we could multiply both sides by 1,000 and multiply both sides by n plus 1, and we would end up with 1,000 on the left side is less than capital N plus 1 on the right side. It's a little easier for me to think in these terms, so I'll say n plus 1 has to be greater than 1,000. Or n has to be greater than 999. Okay? Well, it has to be greater than, not greater than or equal to. So the n we're looking for, we want the smallest n, okay? So the n we're looking for, we're going to use as 1,000. Remember, it has to be an integer. So what this says, this is pretty amazing. This says it takes, and that's all we were really asked for, it takes the first 1,000 terms to get within 1/1000th of the actual sum. Oops, 1/1000th, 0.001 of the actual sum. So, by the way, so if I guess we could use our calculator to do this. You know what? We could also use something like Maple. Okay, we'd have to add up the first. I'm sorry, I'm having all kinds of trouble here. We'd have to add up the first 1,000 terms to get as accurate as we want. That's a lot of terms. This thing converges very slowly. So that would be adding up these terms, which would be 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus, and this would continue, and I believe our last term would actually be minus 1/1000th. And guess what? I actually got out a tool to let me do this, and I came up with approximately 0.693. I've, of course, kind of truncated several of those, but we were interested in this position of that decimal, weren't we? So it took this many terms to get within that value of that decimal, to get into the 1/1000th within that decimal. By the way, the actual value, the actual sum, and we don't know how to do this, so don't be concerned about it, but if we were to actually be able to know what the actual sum is, it's actually the natural log of 2, logarithm of 2, which if we put that in our calculator, we'll find out it's 0.6931478. And of course, there are other terms there, other digits there that we don't have. But you can see our approximation is certainly fairly close to that, but it took 1,000 terms for us to get that close. Amazing. Well, this concludes the idea of how we approximate a convergent alternating series. We'll see things later in this chapter that will help us approximate or find exact values of other types of series. But so far, this is the first time we've been able to do this. Good luck on your homework.